Hello, class. This is Mr. Hart, and in this podcast, I want to start the chapter on energy, work, and power. Okay, some very interesting words that we hear a lot, but may not truly understand what they mean. Okay, so the first thing we want to talk about is energy. Okay, and what is energy? So you may have heard of like energy efficient light bulbs or saving energy or green energy and things like that. But what is energy? What is it really? Is it something that is a substance, or is it some type of lightning that comes out of the light bulb, or what is it? There's a lot of misconceptions about it, and we kind of use it very loosely. But we want to look at what does it really mean to have energy. Okay, and in a physics definition, okay, this is how we describe it. Okay, energy is the ability to do work. Okay. Well, if energy is the ability to do work, then we need to know what work is. And work is the ability to move an object with a force. Okay. So we will come back to energy probably next time. Okay. Let's start with work because it's kind of the foundation for everything else we'll get to. Before we can really understand energy, before we can really understand power, okay, we got to understand what work is. Okay. This ability to move an object with a force. Okay. So think about a scenario. Okay. You're trying to push a crate up a ramp or something like that. You're trying to move some object with some force. Okay. Now, when you do that, you have to do work. Okay. You have to apply a force to make it move. And the farther you move it, the more work you had to do, right? The farther up the ramp you pushed it, the more work that you are doing on this box. Okay. And so we know it's going to be dependent on force, and we know it's going to be dependent on distance. And so when we look at it, it is just that. The work is dependent on the force and the distance. Okay, so work equals the force times the distance. Okay, so W is work, the F is force, and this delta X is change in X, which is the same as distance or displacement. Okay, so simple enough. We just see how much force we are applying. We see how uh, displacement. We see how much force we are applying, and we see how far it went. Okay, simple enough. But again, this is kind of a unique quantity in physics because instead of looking at, well, I put this much force and this is how far it went, we look at those two combined and we figure out how much we had to start with. Okay. So again, this will become more clear as we move along, but we're starting to look at, instead of our ending results, we're starting to look at what we started with, our initial conditions, how much stuff we needed to start with. Okay. So again, I'll make more sense as we go along, but work equals force times the distance that we apply that force. Okay. All right. So if you look at units of work, okay, the units are going to be a Newton times a meter, right? Force is measured in newtons, distance is measured in meters, and so we give this a special name when we call it a joule. Okay, represented by a capital J. And you may have heard that word before, but a joule just means it's just this amount of work that we're doing, or amount of energy. So energy and work, they're both in units of joules. Okay. All right. So let's try and get our heads kind of around what work really is and what it means to do work. So let's think of a scenario. Okay. So let's say this car is stuck in the snow. Okay. And these guys are pushing, trying to get the car out. They're trying to push really hard on this car, but are they doing any work? Okay. Are they doing any work on the car? If you think about it, based on the definition, if work is the force times the distance, okay, change in x, or maybe written as force times the distance, maybe sometimes it's written with a d, okay, force times change in x or force times distance, however you want to think about it. If our change in x or our distance is 0, then no work is being done on the car. Which is kind of weird to think about, right? Because, I mean, these guys are obviously pushing as hard as they can. You would say, oh, they're working really hard. That's kind of an English way of saying that. But in a physics definition, they're they're not doing any work on the car because they're not changing any conditions about the car. Okay, if it's not moving anywhere, you're not really changing its conditions, so you're not really doing any work, okay, on the car. So work naturally means that you're changing conditions about something. So if something's not moving, you're not doing any work on it, okay? So once they start pushing it, then they're doing work because they're changing the conditions on a car, okay? Okay, so hopefully that makes sense. And again, as we kind of look at more scenarios through class, it will start to make sense what work really is. But that's a good visualization of what it's doing, okay? All right, so let's try an example problem with work. Okay, it's pretty simple. A woman pushes a crate a distance of 5 meters with a force of 800 newtons. How much work did the woman do on the crate? Okay, so really simple. 5 meters, okay, is our change in x, or our distance. So 5 meters. And our force was 800 newtons. Okay, so our work is just going to be force times change in x. And so we have both of those, so it's really simple. We just do 5 times 800, which is going to give us 4,000. Okay, simple enough. All right, what are the units going to be? If you remember, newtons times a meter, we could write newtons meters, but instead we're going to write joules. Okay, so 4,000 joules of work. Okay. All right, so hopefully that makes sense. Let's try another one. This one's a little bit trickier, okay, but still a work example. So let's say a man's lifting a 20-kilogram box, okay, so he's maybe putting storage away or something. He lifts it 2 meters into the air, so he picks it off the ground and puts it up on a high shelf or something. How much work did he do on the box? Okay, so you'll notice there's no force listed here. Okay, but we do have the mass of the box. So if you think about the force is actually the weight of the box, because in order to beat that, you have to apply the opposite amount of force up. Okay, so the force is going to be the weight of the box. And if you remember, it's equal to m times g is the weight. So we just plug in 20 in for m. Or oops, try and circle that a little bit better. We'll just plug in 20 for m. And you plug in 9.8 for G. Okay. And when you plug that in, you get my calculator out. 20 times 9.8. You get 196. Okay. So the force is 196 newtons. Okay. And the distance, or the change in x, is going to be 2 meters. Okay, so now we have a force, we have a distance, so we just take the work equals the force times the change in distance, or sorry, the change in x or the distance, which gives us 196 times 2, which gives us, pull out the calculator again, just to make sure. We get 392. 392. And again, this is in joules. Okay. So there you go. So hopefully these are pretty simple to figure out. Okay. And again, we'll see a little bit when we get to energy why these calculations are so useful. Okay. But let me have you try one on your own really quick. If you're doing this for participation, try this question on your own. Okay. So 2014, actually, let me have you do the other one. A 70-kilogram man walks up a flight of stairs. If each stair is 0.21 meters tall and there are 20 stairs, how much work did the man do? Okay, so try and do this one on your own. Again, think about what the force is, think about what the distance is, and see if you can figure out how much work is done. Okay? All right, so let's look at an application. Okay, so one application is bullets. So we talked about these a couple times before when we talked about conservation of momentum and things like that. But let's think about it in terms of work. Okay, so think about, what do you think will make a more accurate boulder or a more accurate bullet? A gun with a longer barrel or a gun with a shorter barrel? Shorter barrel. There we go. Okay, so which will be more accurate, a longer barrel or a shorter barrel? Okay, and so if you think about it, hopefully you realize that the longer barrel is going to be more accurate because this is the change in distance for the longer barrel, and this is the change in distance for the shorter barrel. Okay, so the longer barrel obviously has a longer distance, so it can apply the force of the bullet or force on the bullet for a longer time, okay, or for a longer distance. So the longer barrel is going to be able to do more work, whereas the shorter barrel will not be able to do as much because it doesn't have as much distance to work with. Okay, so if you've ever gone shooting, you'll know that the longer barrels are more accurate because they can apply the same amount of force for a longer distance. Okay, so that's why snipers always have very long barrels for their guns. Okay. All right. The last question I want you to think about is, does angle matter when we're talking about work? Okay. So here's a scenario. This guy's pulling on this crate or something at a certain angle. He has a rope and he's pulling on this crate. Does the angle he pulls it at affect the work? Okay. Think about that for a second. And if you think about that long enough, hopefully you've come to realize that yes, it is going to make a difference. Because if I am pulling on a crate, let's make this really exaggerated. If I'm pulling on a crate like this and I'm trying to move it to the left, okay, this obviously isn't very effective. The amount of force that's going into moving it to the right is very little. Okay, so I'm not doing as much work when I'm pulling it at this angle. The best angle is straight perpendicular like this, okay, because then all your force is going into pushing the crate rather than pushing up on it. Okay, so when you notice when you move things or move furniture, you always push very flat against the box, very perpendicular, because that's the way you can do the most work. And so angle does matter when it comes to work because it changes how much force is going into the movement or the distance. Okay, and if you get into AP Calculus, you'll actually calculate how much it is, but we won't worry about it right now. But I just want you to realize that angle does matter when it comes to force and work. Okay? And the last thing we did in class is we did the work inquiry lab. We wanted to know how does the amount of work that is done on an object affect the speed of the object. Okay? And so make sure you get that lab done in class. But that is it for this week. Hopefully that made sense. And let me know if you have any questions. And thank you for watching.